Example 1, interpreting the slope of a linear model. As dry air moves upward, it expands and cools. If the ground temperature is 20 degrees Celsius at the temperature at a height of 1 kilometers is 10 degrees Celsius, express the temperature T in degrees Celsius as a function of the height h in kilometers, assuming that the linear model is appropriate. So the key thing that we need to look at first is that we're expressing the temperature T as a function of the height h in kilometers. And we're assuming that it's a linear model. So assuming that it's a linear model, we're going to write the slope-intercept form according to temperature. So T is going to equal the slope m times h plus the y-intercept. Now, the first thing we need to look at is the ground temperature. So what does it tell us about the ground temperature? Well, the ground temperature tells us that we have our height and temperature in terms of our ordered pair, and the height of the ground is going to be 0 when the temperature is 20 degrees. So what we want to do is we can figure out what is the y-intercept according to that ordered pair. Well, if we know that the temperature is 20 degrees, and we know at the height of the ground is going to be 0, then we can determine that the y-intercept is 20. So this tells us that this represents the y-intercept. Now we also have a second point. It's telling us that the temperature at height 1 kilometers is 10 degrees Celsius. So that means that we have another ordered pair that tells us when the height is 1, the temperature is 10 degrees. So if we know the y-intercept, we can also find the slope. How do we find the slope? Well, if we look at these 2 points, we can take 20, subtract 10, and then take 0 and subtract 1, which gives us 10 over negative 1. So the slope is negative 1. So now we can determine what our model is, because we know that the y-intercept is 20 and we know that the slope is negative 10. So the model is going to be 10, which is equal to negative t, which is equal to negative 10 times h plus 20. So therefore, there is our mathematical model. So now let's take a look at part B. In part B, they want us to graph the function in part A. So if we want to graph the function in part A, what do we know? We know that the height represents the x-axis and the temperature represents the y-axis. So if we want to graph this, we can look at our ordered pairs. We got 0 and 20, so we know that we have 0 and then 20 is a point on our graph. And we also know that we have a graph where it states 1 and then 10. So what would it be at 2? So if we know that h is 2, then what would t be? So that would be negative 10 times 2 plus 20, which gives us 0. So we know we have 0 here. So let's go ahead and draw our line through here. So there is our function where t is equal to negative 10h plus 20. Now the one thing I want to point out is that the slope, right, is representing the rate of change. And it's important to note that it's negative 10 degrees Celsius per kilometer. So again, there's a rate of change that's going on there. Now, next we want to find, okay, what is the temperature at height of 2.5 kilometers? Well, if we want to find the temperature, knowing that the height is 2.5 kilometers, then we're going to use our model to find the temperature, which is negative 10h plus 20. So if we take T, which is equal to negative 10 times 2.5 plus 20, then what do we get? We get T, which is equal to negative 25 plus 20 degrees Celsius, so that becomes negative 5 degrees Celsius. So what is the temperature at a height of 2.5 kilometers? Well, it's negative 5 degrees. Now, if you look here between 2.5, if we wanted to graph that, you can see that it's going down in that particular direction.